So here we're going to integrate with the help of logs. Let's start off with a quick review. What's the derivative of ln x with respect to x? We know that's just 1 over x, correct? So if we go the other way, what's the integral of 1 over x dx? We might be tempted to say that the derivative is ln x, right? Because we know differentiation and integration are opposites of each other, right? They undo each other. So we might want to say that's the answer, which it sort of is, but one thing we have to keep in mind, what's the domain of 1 over x? 1 over x is a function that's basically continuous everywhere except for x equals 0, right? How does that differ from ln x? Well, if you recall, ln x has a domain of x is greater than 0, right? So this doesn't really make sense if we want to take the integral of 1 over x, because ln x, the answer we get, only applies to the positive. Well, the solution we have for this, essentially, is just to make the integral of 1 over x ln of the absolute value for x. Then we're okay, because, and this should be plus c, obviously. This is an indefinite integral. But basically what this does is anytime x is negative, it makes it positive, which will satisfy having this as the derivative, or as the integral. Now, the other thing to keep in mind is ln x cannot equal 0. X cannot equal 0 as well, which is fine because that's also true of our 1 over x, right? That's the discontinuity. So there is like a restriction on this thing where x clearly cannot equal 0. Okay, so how can we use this fact that the integral of 1 over x is ln of the absolute value of x? Well, if we look at this problem right here, how can we solve this? We know we have something in the denominator, and that's sort of an ugly thing in the denominator that we want to be able to get rid of. Maybe you can see the answer already, but if you can't, u substitution is our friend, right? So in order to make u substitution work, we take the derivative of u, which just ends up being 3. And then what we can do is we can rearrange this for dx. So essentially we can plug this in for dx. So we're going to get 1/3 du is equal to dx, right? If we just rearrange that thing. So let's go ahead and plug that in to this equation here. So we have the integral of 1 over u times dx, which is 1/3 du. Notice how this is an integral with a constant in there, that 1/3. So let's just pull the 1/3 to the outside. And now this looks very similar to what we just had up here, right? The integral of 1 over x, right? In this case, it's 1 over u. But we know that integral evaluates as ln of the absolute value of, not x in this case, ln u. And then we can't forget our plus c, right, because it's an indefinite integral. Then we can make our back substitution for our variable, 1/3 ln, instead of u, we have 3x minus 10, the absolute value of 3x minus 10. There we go. That's the integral. Oh, plus c, can't forget about the plus c, right? So the integral of 1 over x can actually help us a lot with rational functions like this. Let's go to the next one. Actually, you can even try the next one yourself. If you want, pause the video, try it yourself, and see what you get. But here I'm going to go through it as well. So again, my substitution is going to be u equals x squared plus 10. I'm going to choose the denominator here because think about our u substitution. We're always looking for something that has a derivative also inside the function. We know the derivative of x squared is going to be something with an x, right? And that x is on top. So we know maybe if we can take the derivative of this, du by dx equals 2x. And if we rearrange this for something like du equals 2x dx, or even more simply, because I know we're getting a little bit cramped here, but I can rewrite this as essentially 1 over x squared plus 10. Oh, and that's a u. I'm going to replace that with u. 1 over u times x dx, right? So if we can rearrange this substitution to be just x dx, we're golden, right? So this essentially, we can rewrite this as, if we divide both sides by 2, as 1/2 du equals x dx. So now we can make this substitution that x dx can be plugged in, or 1/2 du can be plugged in here. And this is getting a little bit tight. Actually, I'm going to erase this line here. So this gets plugged in as essentially the integral of 1 over u times 1/2 du. Again, that 1/2 gets pulled to the outside, right? So it's just going to be 1/2 of the integral of 1 over u du. And then if we back substitute so we have to take the integral first, that's just going to be 1/2 ln absolute value of u plus c. And then if we back substitute, we're going to get 1/2 ln of x squared plus 10. There we go. Oh, actually, that should be absolute values. I wrote brackets there. These should actually be absolute values, right? And you can always check your answer by just taking the derivative of this. Oh, always forget about the plus c. Don't forget about that plus c at the end. But you can always check your answer by taking the derivative of this. Maybe you realized how to take the integral of this right off the bat, and you saw that this was the answer. But the u substitution provides an easy way to make sure that we get to the right answer without too much messing around. Okay, here's another example of a rational function. Can we integrate this using u substitution like we did in the previous questions? Well, if you think about it, usually in u substitution we're looking for something that has a derivative that's easy to find, right? But if we made the substitution, for example, for what's in the denominator, x squared plus 1, we know the derivative of that's going to be 2x, so we should look for something with an x in it. Unfortunately, the thing in the top is way more complicated than that. So essentially what the approach to a question like this can be is we want to simplify this rational function. We have a way to simplify this rational function, and that is by dividing. If we divide these two polynomials, it can actually give us two things that are separate and a little bit simpler. To see what I mean by that, think about your division statement. We know the dividend divided by the divisor. I know you might be a bit rusty at this, but what this equals is the quotient, which is basically the result of our division, plus the remainder over the divisor, right? So we essentially, what we have, this is the dividend in this question, this is the divisor. So if we divide these two, we're going to get a quotient plus the remainder over the divisor. And the point is, we're going to end up with two separate things that might be easier to integrate than this whole thing right here, right? So again, I'm going to do this off to the side. See if you can squeeze it in on your page somewhere. But essentially what I'm looking for is I'm looking to divide x squared plus x plus 1 by x squared plus 1. Oh, made a mistake there. We can't forget about that 0x term there. That's going to make things more correct when we actually do the division. So let's divide these things. So the first terms, how many times does x squared go into x squared? That's easy, just once, right? And then we can multiply x squared times 1. Well, that whole thing is just x squared plus 0x plus 1. Subtract. Those first terms go away. The second terms, x minus 0x, is just going to be x, and those third terms go away. So basically x plus 0. So we can rewrite this statement up here using this, right? Essentially, x squared plus x plus 1 over x squared plus 1 is just equal to the quotient, which is 1, right? It's the answer to our division problem, plus the remainder, which is x, over the divisor, x squared plus 1. So the question is, can we integrate this thing? And yeah, you should be able to see that we can. So I'm actually going to replug that in over here. We have the integral of 1 plus x over x squared plus 1 dx. And because it's two separate terms, we can actually take the integral of those two things separately, right? So it's essentially going to be the integral of 1 dx plus the integral of x over x squared plus 1 dx. If you want, pause the video here, do that integration yourself. You should be able to do that with what we've learned so far. There you go. So once you've done the integration, I didn't show the steps because it's very similar to the previous questions we did, but the integral of the 1 is just x, and the integral of x over x squared plus 1, if you use u substitution and logarithmic integration, you end up with this. Don't forget about the plus c. We only need to include one plus c here, even though there might have been plus c from here, because both of those c's sort of add up to a single plus c. So I made another mistake in this one. This question is actually the same as the question above it. So I'm going to replace it with one from your textbook, which is 2x over x plus 1 squared dx. You can try this one yourself. Pause the video here, try it yourself. I'm not going to write down the whole solution. I will write down the final answer so you can check against yours. So pause the video here, try it yourself, unpause it to see the final answer. Or you can look in your textbook, it's on page 330. So that is the final answer. The substitution that's probably easiest to make is just to make a substitution for the x plus 1, right? Make u equals to that, and you'll see that it comes out relatively nicely in this form here. So this next question is different because it actually has a ln x in the integral. We're not using ln x to basically take the integral of a rational function. We actually have a ln x in the integral. When that's the case, it's nice to get rid of that ln x, essentially. So an easy substitution to make here is let's let u equal to ln x, and let's just see what happens. So in order to do u substitution, we're going to take the derivative, which is just 1 over x. So rearranging this for dx, we would get du equals 1 over x dx. And you might wonder why I didn't just solve for dx. Well, we can actually rewrite this thing as, well, u to the 5th. And let's move that x in the denominator out to the side. So it's going to be 1 over x dx, right? Well, if we do that, notice how this 1 over x dx matches this 1 over x dx. Beautiful substitution there. So look, it's just going to be the integral, the integral of u to the 5 du. If we make that substitution. Oh my gosh, that's so much easier to take the integral of. We know how to do that. That's just going to be u to the 6 over 6 plus c. That's it. And rewriting this out, back substituting for x is just going to be, oops, not u to the 6. It's going to be ln x to the 6 over 6 plus c. There we go. Not so bad. So when you have a ln or a log inside your integral, it's actually pretty good. It works out pretty nicely a lot of the time, as long as there's nothing crazy going on in the integral, to plug in u as ln x. This last one, you might be wondering how it has to do with any of the other questions. Well, the integral of tan x dx is not something we've covered, and it's not obvious what the integral of that is. It's not like one of our trig functions. If we take the derivative of it, we're going to get tan x, right? There's nothing obvious. So we are able to come up with integrals of sine and cos. So a good first step here, why don't we just make tan equal sine x over cos x? Use one of our identities, right? If that's the case, can we now use what we know about integrals of logs in order to help us out here? Well, think about this. We have on the bottom cos x. And what's the derivative of cos x? Well, it's negative sine x, right? Which resembles what happens in the numerator, right? So essentially the key to figuring out when we can use this type of substitution with logs, it's when we have something like u, and on top of it we have the derivative of it. So this is sort of the key of when we can use a substitution with logs or with ln. That's just sort of like a little hint there. So the u substitution we can make here is in the denominator, because the top thing is the derivative at the bottom. So u equals cos x du by dx equals negative sine x. And again, here we can sort of rearrange a little bit to make the substitution easier. So I'm looking to rearrange this thing so that either the sine or the cos will cancel out, right? And I can do that by, if I bring the dx to the other side, I'm going to get du equals negative sine x dx, right? And look what's in the top. We have sine x dx. Okay, well, we have the negative here. Easily we can just move that negative to this side, right? And I'm just going to scratch it out here. So that negative goes on the other side, so we can replace this sine x dx with negative du, right? So let's do that. Negative du over, and then the cos x, the substitution was u, right? Simplifying this a little bit, we'll bring the negative outside the integral, 1 over u du. There we go. We've taken the integral of this already multiple times, right? So this is just going to equal negative ln absolute value of u plus c. If we back substitute for u, ln of u is just cos x, right? Absolute value of cos x plus c. There we go. That's not so bad. Now this isn't something you necessarily memorize, that the integral of tan is negative ln cos x plus c, but it isn't that hard to find, as long as you can recognize that we can use u substitution with ln here.